So we have discussed two ways to analyze amino acids at this point, and one was the electrophoresis chamber, where we take a gel slab or maybe a sheet of paper or some kind of media, and we kind of span it between two compartments, a negative and a positive, and we allow the voltage to basically pull the amino acids away from each other. And all of the separation at that point depended on the pi values. So we were really playing off of charges with the electrophoresis chamber. We then spoke about the TLC method, the thin layer chromatography, where I take another sheet of paper or a TLC plate and I spot my component on it that could be a single amino acid or maybe many amino acids, a mixture, and we allow the mobile phase and the stationary phase to kind of juggle the amino acids with each other, and they begin to separate based on polarity. And now we're going to talk about the third method to separate amino acids, and that's ion chromatography. So if you've started with our program in the very beginnings, one of the very first instruments that you used in our general chemistry course was an ion chromatograph. And if you go back and you pull out that lab basically consisted of you taking toothpaste and basically making a solution of the toothpaste, extracting it, and injecting that sample onto our ion chromatograph system. You were looking for fluoride content at the time, and you wanted to compare that to the label. So ion chromatography is not new to some of you, but again, if you've started maybe midway through our program, or if you're adding in, or maybe this is the only class that you're taking in the program, we want to take a few minutes and explain what ion chromatography is and how it does its job. For many of you this semester, you're taking this course along with our first or our second instrumentation class, and that second instrumentation class will consist of ion chromatography lecture. So you're probably going to get a double dip in the world of IC, and if so, that's okay, because the more exposure that we have, the better off we're going to be. So I first want to talk about ion chromatography. Just like thin layer chromatography, this is separation again. So we're going to see that ion chromatography will separate the amino acids from each other, just like TLC did, but we're playing off of ions here, and when we play off of ions, we're looking at charges again. So we kind of already discuss the whole concept of these amino acids carrying a charge. They carry a positive charge or negative charge depending on their pH. So yet again, we're seeing kind of a pH dependency here that we have to put into place if we want to analyze these amino acids. So it's not uncommon to see some type of buffer solution being used, and we've spoken about buffers. We kind of know the idea of buffers. If you're uncomfortable with buffers, go back to that general chemistry text or go back to our YouTube videos where we talked about acid and base chemistry in Organic Chemistry 1, and you will see a couple of videos there concerning buffers and buffer solutions. So we typically make a buffer and we put it on this machine and we help control the pH. That's the purpose of the buffer. So we know that maybe we want a pH of 2 or a pH of 6 or a pH of 10. We will make a buffer that will make sure that that pH value doesn't change too much along the course of the separation within the system itself. Not only that, but we can change the pH as we go from start to end of the separation as well. So we can start with pH maybe of 2, and then we can kind of upgrade that to pH of 10 at the end of the analysis, and we can change the pH values as the separation begins to happen in the instrument. IC does its job a couple of different ways. You're looking at ions here, and it's very important to understand that ions can be cations and they can be anions. And cations are positively charged and anions are negatively charged. So on chromatography, it's kind of opened its door up to everybody that wants to participate. The only thing is that you've got to choose the correct stationary phase. So here again, just like with TLC, we have a mobile phase in place and we have a stationary phase in place. The mobile phase is very similar to what we've discussed with TLC. This is a solution that typically you have made or that you have ordered a standard of. And this solution is going to be a pH controlled solution, and this is going to basically push your components through a column in this case. So we're looking at a mobile phase, and the mobile phase will push the component through a column, and that column has stationary phase on the inside of it. And that stationary phase can come in two forms. We can have a cation exchange, and we can have an anion exchange. And that kind of makes sense, right? I mean, if we can analyze cations and anions with the IC instrument, then that probably means that our stationary phase should be able to handle a cation exchange or an anion exchange. So let's pause for a few minutes and kind of think about what's going on inside of this column. So let's say that this is the wall of the column, and off of this I get some stationary phase. Now this stationary phase could be silica, it could be alumina, it could be some kind of carbon chain with benzene rings on it. I mean, it could be a doozy. So I'm just going to represent it with dots. And off of this stationary phase, we can modify the groups that are existing there. And this is what determines the difference between a cation column and an anion column. And off of these groups, off of this structure, let's say that we want to exchange cations. Well, okay, that means I need something that will attract the cations to the stationary phase. And one of our poisons of choice is SO3 groups. So if I can put an SO3 group there, I've got these oxygens with these electron pairs, I've got this thing that carries a negative charge with it. Well, what begins to happen is that it serves as a magnet. And these SO3 groups will just kind of hang out, and these positive cations that begin to come through the actual column itself, so positive, 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 they begin to get attracted to these negative SO3 groups, and they kind of hang out for a while. They go on a date, they have a good time, and then there comes a point where they have to break up, and they say, I'm sorry, this is not going to work out. The mobile phase keeps interfering, so the mobile phase is going to push me along, and I'm going to gradually travel through the column and then out the other end. Well, that's the cation version. We have a cation version that has SO3 groups on it. So once again, you need to take a look at these SO3 groups and understand that those are negative. However, the purpose of those negatives are to attract positives. So you're separating the positive cations that go through, and that is why we call this the cation column or the cation exchange. Now, on the other side, if we can separate cations, we should be able to separate anions as well. So SO3 is not going to do that for us. The SO3 group is going to cause a problem because that's only going to attract positive anions or positive ions. In the anion column, we have to substitute that SO3 group for something else. And we need something positive because we need something that will attract the anions toward the column. So instead of SO3, typically this is going to be a nitrogen-containing molecule, and this is kind of a quaternary ammonium in a way. So this N, and I'm just going to put CH2 parentheses CH3 3, and this whole thing carries a positive charge. You can draw that if you want, or I'm perfectly okay with you just doing this number. And if you aren't happy with that, I'm okay with you doing this number. So put an R there for random group. Typically, these are very small. They're very small R groups that get sandwiched onto the nitrogen, and hence that's why we see a CH2 group with 3 CH3 groups on there. Okay, so there's the basics of anion chromatography. We have something positive on the column, and then if we have negatives, negatives are anions that come through the column, what you see is an attraction that begins to happen with the stationary phase and the components that I want to separate. Just like in the cation story, except this time we're pulling in negatives. We're pulling in anions here. Okay, so this is called an anion column or anion exchange. So you got to be very, very careful, especially on the test, maybe when I ask you to explain how ion chromatography works concerning amino acids. You want to talk about the column, and you want to say in the cation column we are attracting cations. Therefore, the stationary phase needs to be negative. In the anion column, we want to separate anions. So therefore, the stationary phase has to be positive. So that's the difference between an anion and cation column. Notice that we're playing off of charges here. So that's what this whole thing kind of relies on. We're looking at charges, and these charges are very important because all of the amino acids will have different strengths. The stronger that they are, the longer that they stay in the column. And this is what gives me the separation. So if I'm looking at these charges, the more charged that they are, or the more polar that they are, the more they hang out with the stationary phase most of the time, and the longer that they stay in the column, well, other things that race through the column can come out first. And this is what gives me my separation within the field of ion chromatography. Now, if I take a look at maybe a picture of some stationary phase, this is what I could see. So this is a big fat stationary phase example, and off of it I see these SO3 minuses. These SO3 minuses have on them Na pluses, and that's because that's the way it will come in the very beginning. So we call it cation exchange because the cations that we have incorporated into this mixture will come in and kick the sodium off and exchanges places with the sodium, and that is why we call it a cation exchange. So this SO3 minus is negative. It attracts more positives. The positive is a big bully, and it comes in and it kicks sodium off, and it takes sodium's spot for just a few seconds, and then it will hop down to the next SO3 group, and then it hops down to the next SO3 group, and then it will keep doing that until it leaves the column in the very end. But there is an example of the stationary phase for ion chromatography. There is a modification for ion chromatography. We call this the amino acid analyzer. And the amino acid analyzer is an instrument that basically automates this whole process. It is kind of a special form of HPLC or IC. And what they do is that at the very end of the separation process, they mix ninhydrin with the amino acids. And we've spoken about the importance of ninhydrin. It says that it turns things purple. And we can use this as a detection so that when we separate amino acids, they come out of the machine, they react with ninhydrin, they turn purple, and we can use a detector to kind of monitor that for us. And we can kind of see spikes of chromatograms, and then the height of the spike, of course, represents how much amino acid that you have in your sample. Here is a picture of an amino acid analyzer chromatogram. Notice they start off with a pH of about 3.3, and then they change it after a couple of mils have been pumped through, and then they change it again after more mils have been pumped through. Notice the height of the peaks. That kind of corresponds to the amino acids that were found. The problem with the amino acid analyzers, however, is that they are very messy. If they spring a leak, well, you're going to get an anhydride everywhere and everything begins to turn purple. So if you're working on an amino acid analyzer, you will look like a Smurf by the time you are done, and this is something that people just really don't find attractive. So there's the amino acid analyzer. Take a look at it. Very similar to IC.